function of exercising muscle. Okay, some of this should recap for you. Okay, in terms of types of muscle, we've got smooth muscles found in like blood vessels. Okay, involuntary muscle, controlled very much so by the autonomic nervous system, the parasympathetics. Like I said, again, the walls of blood vessels, direct internal organs. We obviously have cardiac muscle, speaks for itself, the heart. Okay, that's obviously again controlled by the autonomic nervous system. Parasympathetics, we'll see a lot more about in other lectures. And also the endocrine system as well. Okay, and then we have skeletal muscle, which is pretty much where we're going to concentrate on. Okay, this is voluntary muscle. Basic structure of skeletal muscle. Okay, this is a schematic in your book. What's it about? Tendon, the muscle attaching to the tendon and the bone. I don't care whether you know or you do know about the different connective sheaths. Connective sheaths here, the epimysium, the endomysium, perimysium. Physiology is a big word. Just understand that within each muscle fibre you have these myofibrils. And these muscle fibres are multinucleated. Okay? So more than one nucleus, multinucleated, and we have our myofibrils within our muscle fibre. So, a schematic here of the structure of a single muscle fibre. Lots of mitochondria, again, very metabolic cell, just like neurons. Here's our myofibrils. Okay. Here's our plasma lemma, or the plasma membrane of the cell, of the cytoplasm. We have the transverse tubules, T-tubules, okay, which proceed inwards. Okay, they become important. And we have the cytoplasmic reticulum and the terminal cisternae. What's the purpose of the transverse tubules?
Carry action potential.
Yeah, good. Carry the action potential into the muscle cell, okay, from the plasma lemma. Okay. How about the cytoplasmic reticulum? Well, yeah, it's where the muscle stores calcium. Okay? Terminal cisternae here, which kind of abuts the transverse tubules and T-tubules, is really a continuation of the cytoplasmic reticulum. And that's where the calcium is released from into the cytoplasm inside of the cell. Okay? That's been known also as a fenestrated reticulum. You book uses the term terminal cisternae, so we'll use that. Okay? Okay, so that's just 2 points there. That's a micrographic shows the myofibrils. Here's our myofibrils, for instance, okay? One here, one here. We've got striated patterns occurring in the muscle fibers. We'll talk about that. These yellow brown things are fat droplets. Okay? Here's some nicer shots. So you can see skeletal muscle is very, very striated. Okay? Very, very striated. So here, for instance, you have striated skeletal muscle, or the muscle cell itself. You have the blood vessel, okay, and you have the connective tissue. Similar one over here. These will be nicely budded muscle fibers. And again, here's a muscle fiber right here. Here's a muscle fiber right here. You've got basal membrane, etc., etc. Here's a cross section here of the muscle fiber. Here's the myofibrils, all located pointing out. Okay, that's a really this is where the contraction occurs, and we'll break that down in a second to see that. Okay, in terms of the sarcomere then, functional unit of the myofibril, which makes up obviously your muscle fiber, is thousands of myofibrils, individual myofibrils within a muscle fiber. Okay? So the sarcomere contains the contractile elements, that's important. The contractile elements, okay, between each pair of Z, where I come from, Z, right? Discs. Discs are proteins. Okay? They're proteins. And physiologists like to make your life difficult by having all these different bands. Okay? I bands, A bands, H zones, M lines. I don't care when you know that. It's not important to us. Okay, maybe when you did 215 if it was. Okay, I've taught physiology class before, we went through all this. For this class, I don't care. It is in your book. Okay? But we've got more other important things to consider, okay, in terms of the structure of the sarcomere, the actual structural unit, okay, of the muscle. So, excuse me. Here is, for instance, here's a Z disc or a protein, runs right here. Another one right here. And the sarcomere, by definition, occurs between each Z disc. Okay? Here's all your different zones, don't care if you know those. Okay? Making up the sarcomere is your actin and your myosin. Your actin is your thin filament. Your myosin is your thick filament. Okay? And we can break that down, blow it up if you like. So here we now, from this section blown up, is our sarcomere, Z disc. Okay? It's a Z disc. And as you can see, there's a lot of stuff going on here. Very busy. Okay? So, to kick off with, we have the actin, okay? Thin filaments. That is attached to the Z disc, the Z protein. Okay? We also have our thick filament, myosin. That is also attached to the Z disc. It's attached to the Z disc by the structural protein, for instance, one's called titin. Okay? Another protein, structural protein. In terms of the actin, the thin filament, we also have another structural protein that kind of holds everything together, and that's called nebula. Okay? All right, so we have between each from each Z disc, we have then actin, thin filament, myosin. Look at those in more depth. Here now is the thin filament, the actin, made up of G-actin or globular actin. Tropomyosin, remember these are all proteins. Tropomyosin is weaving its way through. This is blue snake-like material. And troponin, green, a protein. We've got troponin overlaying tropomyosin, it's weaving its way through the globular actin, the G-actin. Okay? So that's the thin filament. The thick filament is this myosin molecule. It looks like a toilet bowl brush, right? With all these heads, these golf, basically we've got a whole bunch of golf clubs, right? These heads. The purpose of the heads come up and actually attach to the thin filament at strategic points, which we'll discuss in a second. Okay. And these heads, very important, these heads have two binding sites. Okay? So, the head coming up. Okay, and two binding sites. This is myosin. It has obviously an actin binding site. Okay? Obviously, to bind the actin. Okay? It also has a site where it will break down ATP. That's ATP binding site. Nestled in that binding site, an enzyme called ATPase. Okay? And that becomes important to us. Two binding sites. Active binding site and a binding site that can break down ATP into ADP and organic phosphate. So those are the key points. Like I said, I don't go through the key points, so those are there for you. Okay? It lays it out there in terms of myofibril, the reference to sarcomere, the myosin, and the thin filament. Yeah. We've already already spoken about the outer motor neuron in the last lecture, so I'm going to leave that now. But I want to talk about, the reason I was really going to talk about that little section there, the events leading up to muscle fiber contraction. We've already spoken about this, right? We said at the neuromuscular junction, acetylcholine is released. We went through that in the last lecture. Okay? It binds to receptors on the sarcolemma. And as you know now, enough acetylcholine binds to those receptors, and action potential is transmitted the full length of the muscle fiber. I'm going to go through this schematic in a second. The action potential then triggers the release of calcium, cytoplasmic reticulum. Calcium binds to troponin on the active filament, and troponin forms tropomyosin, that blue protein, of the active sites. I told you to get okay? Allowing myosin heads to attach to the active filament. Okay, so like I said, we have the calcium being released from the cytoplasmic reticulum, right? Remember? Okay. So when the calcium is released into the inside of the muscle cell, it binds to troponin. When it binds to troponin, troponin moves off and pulls with it tropomyosin off the myosin binding site. So then myosin can come up and bind. So on the thin filament then, underneath troponin and then tropomyosin is the myosin binding site. Okay? So again, we'll go through this schematic in a second. With calcium activation, myosin heads bind to actin, resulting in a conformational change in what we call a cross bridge. Cross bridge is when the myosin head comes up and binds to the actin. Cross bridge. Okay? The myosin head tilts toward the arm of the cross bridge, towards the inside of the sarcomere, and drags the actin towards the center of the sarcomere. The tilt myosin head is known as a power stroke. Okay? And the pulling of the actin filament past the myosin filament results in shortening of the sarcomere and the generation of muscle force. Again, I've got a schematic. Enough. Those are all those different bands, which I don't care about whether you know or not. Okay, it's going to talk to us in this class. Obviously, the only thing this is showing is that here's the muscle relaxed, right? Here's the Z-discs. Sarcomere shortens with contraction. So a lot of those zones change, right? And then we've got even very closer here with a maximally contracted muscle. One thing I did want to mention is we spoke about the neurotransmitters being released at the neuromuscular junction, right? We said acetylcholine is released in the last lecture. And that binds to those chemically gated receptors on the postsynaptic side, on the muscle, remember? Okay? And then we've got, if they bind to the receptor, we've got sodium coming in. That brings a positive charge, changes the resting membrane potential, we generate an action potential. That propagates down the sarcolemma, the plasma membrane of the muscle cell, right? And then down the T-tubule. That's what this guy is, right? T-tubule. Okay? How does it propagate down the sarcolemma? It propagates down the sarcolemma because what it does, there's lots and lots of voltage gated channels all the way down the sarcolemma. So what's happening is that voltage is then triggering these gates to open up, these voltage gated sodium channels, not chemically gated voltage channels that we have here. Because it's binding acetylcholine, that doesn't happen here. Because we've got a positive charge coming here, that changes the rest of the membrane potential here, 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 here. So the trojan coming in again here. Actually, another action potential firing here, here, here. It jumps down. Okay. And then we have channels on the T2 block. Okay. And these respond to a change. These respond to the calcium. Sorry, these respond to the voltage coming down the T2 wheel. So the voltage coming down the T2 wheel will trigger these calcium channels, okay, to open up. You know, calcium is stored in the cytoplasmic reticulum. To open up and let calcium out into cell membrane. Okay? It does get complicated if you kind of follow the events, okay? Chemically gated ion channels, voltage gated ion channels, propagation of the action potential. The action potential triggers the opening of calcium channels. Called ryanodine receptors, open to let calcium out inside of the muscle cell, okay. Pulling and then bind that calcium, as you know, then is binding to troponin. And then we go on with the events I just described. Okay. In terms of the molecular events of the cross-bridge cycling in skeletal muscle, okay, in terms of the actin pillars during contraction. So there's our myosin head. So we've just got one myosin head here, right? So as you know, thousands of them. Okay. At this present time, we've got ADP, calcium triphosphate, inorganic phosphate, in that nestled in that binding site. Okay. So we've got cross-bridge attachment. The power stroke, shortening, muscle contraction, ADP, and inorganic phosphate are released. With the power stroke, the myosin head bends it towards the action pillar. Okay. Now, how do you detach the myosin head? The myosin head is detached when ATP comes in and binds. Okay? So it binds into the actin binding site. Okay? And then we get release of the myosin head from the actin. But it requires ATP. If you've gone to a morgue, dead bodies, right? Rigor mortis. Stiff. Muscles are contracted, right? Why are they contracted? Because your body is not producing ATP. Your body's not producing ATP, but you can't detach the myosin heads from the actin. Makes sense, right? So they'll always stay attached. That's what rigor mortis is. So in the cross-bridge, we have cross-bridge detachment, and we get hydrolyzation of the ATP again, ADP into the eye, and then the process continues. Remember, with the power stroke, you've got the shortening of the cycle. So that's a schematic from another book, pretty much what I've shown here about the action potential being propagated down the plasma lemma here, down into the tubule, where the cytoplasmic reticulum, calcium being released. Calcium binding to troponin, okay? So the binding of the myosin with the actin head, the power stroke is coming through. We want to return to a resting state. One, you have detachment, of course, of the myosin from the actin. Yeah. Okay. Cross bridge has been broken. Also, we have removal of all that calcium that's floating around inside the muscle cell. It's pumped back into the cytoplasmic reticulum. And it's pumped against the concentration gradient, so it requires ATP. It requires energy. Another reason why lots of ATP. Okay? So we need ATP to detach the cross bridge. We need ATP to pump calcium back into the cytoplasmic reticulum. That's important. Okay? Then we have tropomyosin blockage restored, contraction ends, and muscle fiber relaxes. Okay. So ATP is very important. That's kind of another busy slide here showing you showing you that basically there's different types of troponin. This is actually cardiac muscle, but it could be the same skeletal muscle. There's different types. We call isoforms of troponin. There's troponin I, troponin C, and there's larger troponin from myosin. there's different types of tropomyosin as well, so it can get complicated. Okay, just some points. So let me read those through. We'll zoom through those. That's a beautiful shot here of a scanning electron micrographic shot of a muscle fiber, all the myofibrils here, and you can see the actin and the myosin, in particular the myosin here, all these kind of like these toilet bowl brush heads here. That's the myosin heads. It's a beautiful scanning electron microscopic shot. Okay, just to show you that I'm not making this stuff up. Right? Okay, that's beautiful. Okay, muscle biopsies. I want to talk a little bit about muscle biopsies. Okay, what is a muscle biopsy? Well, a muscle biopsy basically is you're walking down to the biochemistry lab. I teach exercise biochemistry, and we can go at the graduate level. We can go in and actually biopsy a sample of muscle. Okay, we can do it. Some people say it's painful. Some people say it isn't painful. Depends on the pain threshold. Women do better than men. Okay. It only requires a local anesthetic, lidocaine. Okay, just on the side. So that it's still some of the muscle. We can do a lot of things with this sample. Okay, so there's an example here. Let's look at the sample here. What's that we can do with this? So as exercise physiologists, it actually becomes important to us. The reason it becomes important is that we can look at fibre type. We can discern fibre type of a person, the proportion of fast twitch and slow twitch muscle fibers. We can also discern whether you have high glycogen content or low glycogen content in the muscle. Now, the actual process can get tricky, okay? So when you've got those sections, basically, we put these sections into different types of mediums, whether it's an acidic medium or an alkaline medium. But if we, for instance, we pre-incubate that muscle section into an acid medium of pH of 4.3, very acidic, what that does, that denatures the enzyme in fast twitch muscle fibers. That enzyme is that ATPase I spoke about in myosin. So it denatures that, breaks it down. It allows various reactions to deposit cobalt, which is kind of a black material, into the slow twitch fibers where the myosin ATPase is still active, hasn't been denatured. You denature the slow twitch muscle fiber with an alkaline bar, high pH. Okay? But you don't really need to know that too much. Basically what we can look at is the fiber typing. We can then look at this under a microscope, and in this case here, we can look at the proportion of fast twitch to slow twitch. In this case, the slow twitch, look at all the cobalt, deposited and count the number of slow twitches. Okay? Or we put in an alkaline bar, we fast twitch. Okay? Slow twitch and fast twitch fiber types, like their name, have a difference in their speed, obviously their speed of contraction. What we mean by that is the different forms of myosin ATPase. So a fast twitch muscle fiber will have a fast isoform of myosin ATPase, and it splits ATP very, very quickly. Meaning the detachment of the myosin head from the actin is very, very quick. Compared to a slow twitch, which has a slow form of myosin ATPase. And remember that ATPase is found on the myosin head. Remember? Okay. That's this one here, that's the fiber typing. This one down here is using a different type of technique. We use a staining technique, and we can also look at the glycogen content of the muscle as well. Okay. Very useful technique. Done routinely around the world in exercise physiology labs, exercise biochemistry labs, etc. Okay, in terms of muscle fiber types, then, again, most of this you should know already. We've got slow twitch fibers, type 1. You can find about 50% in our body. The oxidative muscle fibers, right? We have the fast twitch fibers, the type 2. We have the type 2A, about 25%. We have fast, oxidative, or glycolytic, or glycolytic fibers. Those are at intermediate, intermediate type 2A. We have the type 2X in humans, again about 25%. They're called type 2B in animals. We do an animal, we have type 2B. There's actually a type 2C as well, it's about 2%. About 3%. And remember, the percentage of each muscle fiber is variable, each fiber type is variable among muscles. Among individuals, obviously with exercise training. Sprinters are going to have a portion of, obviously, type 2X, right? Okay, so the endurance athlete is going to have to put on more slow twitch and type 2A. Okay? Here's another shot under the microscope. This is from your book of the type 2-1 there in black. This again, from muscle biopsy, type 2 in black, type 2A white. Okay, good look at white, and then type 2X to the red. Okay.
If you're born with more slow twitch fibers, can you train your body to convert more to fast twitch? Can you ever change that?
You can change, but it's a small change. Genetically, you're fixed. But you can change with training. Okay, you can. It's a relatively small change. Considering what you're born with. Okay. Aging will change. Will change things. Endurance training will change things. Some different types of training will change. Resistance training. We'll see that. Determination of myosin isoforms. This is actually a schematic out of your book here. So those myosin isoforms, right? The fast or slow forms. Okay, we can look at those as well. And we look at them by for electrophoretic separation, which is gel electrophoresis in the biochemistry lab. And what we're looking at here, they're all proteins, right? Myosin proteins. So separation of the proteins done by staining. So these are proteins that are based on molecular weight. So we determine a myosin isoform for particular fiber type. Okay? So that's another thing we can do. In terms of classification of muscle fiber types, again, you've probably just seen something like this before in terms of type 1, type 2A, the intermediate, and type 2X. This is what we call them. Systems in terms of their characteristics. Obviously the type 1 goes really fast, a high oxidative capacity, low glycolytic capacity, contractile speed is obviously slow, fatigue resistance is high, go all day, right? Endurance athletes have a lot of these, and their motor unit strength is low. You start moving up to the fast twitch, the intermediates, very fast twitch, then in terms of the oxidative capacity, in terms of the intermediates, is moderately high, low in terms of type 2X, and then the glycolytics, contractile speed, fast, fatigue resistance, certainly for the type 2X, low, and motor unit strength, of course, is high. Okay? This is really just talking about what I spoke about before in the last lecture, motor neuron size, right? The slow twitch motor neurons have a smaller neuron size, diameter, fast twitch larger. And therefore, because they're larger, the nerve conduction velocity is faster. And to some speeds, we've already spoken about myosin ATPase, fast, slow. What else can we do with our muscle? Well, we can also look at single muscle fiber physiology. It takes a lot of expensive equipment to do this, but we can dissect out muscle fibers and determine their peak force. As you'd expect, peak power is different between muscle fibers. So peak power is obviously going to be higher in type 2X compared to type 2A compared with type 1. So yes, with these muscle fibers, we dissect the fibers out of the biopsy, suspend the sample between force transducers, and measure its strength, and therefore its single fiber contractile velocity. And all fiber types tend to reach their peak power about 20% of peak force, as you can see. 0 to 100% here at peak force, and they're all reaching their peak force of about 20%. Okay, so again, there's the key points for you. We'll read those. Okay. Question came up about fiber type. It's genetically determined for the most part. It is determined by the alpha motor neuron that innervates the muscle fibers. Remember I said fast twitch motor neurons innervate fast twitch muscle fibers. Not a mix. Slow twitch will innervate slow twitch. Okay? Endurance training, strength training, and muscular inactivity may cause a shift in the myosin isoforms. So with exercise training, for instance, particularly with the endurance and strength training, you get a decrease in the very fast twitch, the type 2XB, and therefore you're going to get an important increase in the type 2A, the intermediate fibers. So it can shift. Okay, it can shift. Aging, unfortunately, will also shift. You get a decrease in type 2 and an increase in the type 1. If you like it or not. Okay. Okay, motor unit recruitment. I spoke about this earlier. Principles of recruitment. Motor units are activated on the basis of a fixed order, going from type 1, slow twitch, smaller neurons. Type 2A, type 2X. That's how they recruit. Okay. Type 1 first, type 2A, then type 2X. And that's related to the size principle, right? Although the motor unit recruitment is directly related to the motor neuron size. Okay, just step back one slide. There's that smaller motor unit. Next largest, then largest. Which means then slow twitch fibers, which have smaller motor units, are recruited before fast twitch fibers. So there's light exercise, so maximum exercise. Slow twitch are obviously recruited first, then your intermediates, you have 2As, and then your very fast. Okay? And you're progressing towards maximum exercise. Points. I'm not going to go through this table really. This is table 1.3, percentage of cross-sectional areas of type 1 and type 2 fibers in selected muscle male and female athletes. As you would expect, for instance, in sprint runners, whether it's male or female, they're going to have a high proportion of obviously type 2 compared to type 1. And the distance runners are going to have a high proportion of type 1, slow twitch, compared obviously to the type 2 or fast twitch. you go through down there, or you know, you get down to a triathlete, swims, runs, and bikes, and they're still going to have a high proportion of the type 1, but they've got a fair amount of type 2. Points of brain. Okay, just want to finish off then on types of muscle contraction. Okay. As you've all probably seen before, 3 types of muscle contraction are concentric. Okay. Muscle shortening, isometric, also generated by the length of the muscle unchanged, and the eccentric contraction, muscle length. Okay, also generated by the muscle length. Variation, force reduction with frequency of stimulation. Okay. Single movement unit. Single movement unit exert varying levels of force depending on the frequency at which it is stimulated, meaning the action potential. How quickly those action potentials are moving down on the alpha motor neuron, from the axon hill. Okay? So here, for instance, there's quite a lot of space between the impulses, right? A lot of time between the impulses. So this is a gradient potential. It will reach the threshold, we will fire an action potential eventually, right? If that motor unit, that muscle fiber is continually being stimulated by the alpha motor neuron, okay? You're going to reach a situation we call tetanus, continual stimulation. Huge summation, and you're going to reach your tension your peak tension very, very quickly. Which makes sense. You demand it. Okay? So tetanus means continual stimulation. You go way above your peak tension, generate a tremendous amount of force. But that's dependent on whether you need it or not, right? That's dependent on the alpha motor neuron. What's coming down from the axon hill. Flying down the hill. But you can't keep that up, can you? Because you're going to fatigue. You're going to run out of ATP, all sorts of and fuel, and etc., etc. So it's a short-lived process. Force variation with changes in sarcomere length. There is an optimal sarcomere length. We have optimal overlap between the actin and myosin and cross bridge. Okay? So here if you have developed tension in sarcomere length, okay, and you can see C and D is where you have optimum overlap between the myosin and actin. You think, well, there seems to be optimum overlap between D and E here. Well, it looks like there is. In fact, you can only contract so far, right? You can't contract anymore. So B and C is really the optimum amount of overlap to get to generate that contraction. Okay, it's going right here. So the optimal method of each muscle fiber relative to the ability to generate force. Okay? The optimal sarcomere length is defined as that length where there is optimal overlap of the big and big filaments. Okay? And that maximizes that cross-bridge interaction. Okay, I'm not going to worry about that slide. Those are the key points. Okay. All right. So those are the 2 lectures. So on Wednesday then you will have 2 quizzes. I'll have one worth 5 points, okay, over the first lecture, the neural stuff, then I'll have another quiz on this material. There'll be true, false, put in the blanks, you know your stuff, we'll do it quick. Come properly to class, we'll do the beginner class, grade them, and then we'll get on with the lectures. Okay? Alright. Those of you who are doing 535, can you stay behind for me, please?